Hey, welcome. It's very good to see such a diverse set of JVM engineers in our studio. So let me start with a bit of a provocative question. I know that there are people representing OpenJ9 here, and there are people representing OpenJ9 here. So when is it going to become the same thing, JVM convergence?
Well, I actually don't even want that. I think a little competition is good, and it has always been with OpenJDK hotspot would have never been where it is now without the strong competition from IBM and OpenJ9. So I'm happy that the colleagues are pushing hard so that we have to answer to their optimizations. And I'm particularly happy to have another talk about OpenJ9 here in the program. We had great speakers from IBM before in the past years, Dan Heidinga, Charlie Gracie, Toby Agila. And I'm very happy to have, I would say, the new generation of developers from OpenJ9 here now. It's particularly interesting time because just yesterday, Mark Studley, the OMR project lead, announced that IBM will support public and certified OpenJ9 builds in the future. So that's very good. So let me quickly introduce Igor, who studied at the University of Waterloo and works, as Gleb said, on OpenJ9 since quite some years. I saw that he worked in JIT as a service, which is also a very exciting topic currently with the containerized use of Java. Jonathan Oommen studied at Carleton University, also works for quite some years now on OpenJ9. He worked a lot on memory footprint reduction, for example, also very interesting for containerized Java usage. So I think we have two real good experts here, and today they will speak about some secret GC tunings they did. So let's hear what they have to say. So please get it started, Igor.
Go.
Awesome. Thank you so much, Walter. So good morning, good afternoon, good evening from wherever you are. So today, like we were saying, we're going to be sharing with you some really cool stuff we've been doing here at OpenJ9. So let's just get started. So this is just important disclaimer saying this presentation is just for information purposes. So the outline for our talk, I'm gonna run quickly through what garbage collection is because I would assume people that's listening to this talk know what it is already. And then we're gonna go to the bulk of the talk, which is the advanced things that we've been doing here. So the first one's dynamic breadth-first scan ordering. The second one, double map Arraylights, and finally off-heap management. So a little bit about me. I'm a software developer at IBM. I completed my master's from Waterloo. I'm interested in systems, compilers, machine learning, AI, and I'm a tennis addict, even played professionally before. And a little bit about John. He's a VM GC developer at IBM as well. He studied system engineer at Carleton University. He's mostly interested in machine learning, AI, blockchain, technology, and GC. And a fun fact, he's the second youngest of 11 children. That's a lot of children. Cool. So if you want to get builds from OpenJ9, you can go to adopt.jdk. You can also get a hotspot there if you want to play around with them. It's a great place to get those. So OpenJ9. So OpenJ9 is a fairly mature project, came to the open on 2017. And a fun fact about OpenJ9 is that it actually started as an embedded JVM. You're familiar with the Java micro edition? That's how OpenJ9 started. So very small, and which is one of the reasons why it has some really good memory footprint performance. Cool. So garbage collection. I'll really go quickly on this section here. So garbage collection is a form of automatic memory management, right? As opposed to other programming languages like C++, where you have to manually allocate and deallocate memory. So some of the responsibilities of garbage collection, right? Allocates memory, identifies the liveness of data, and all that data that's not considered live is going to be considered garbage, therefore reclaimed by the GC. So some positives of garbage collection. So it's automatic memory management, right? Helps reduce some certain categories of bugs like double freeze, dangly pointers, right? Which is great. But on the other hand, you have some negatives. It requires additional resources, additional CPU cycles, more memory, can cause unpredictable pauses, those famous stop the roll pauses, and may introduce runtime costs, and the application has little control of when memory is reclaimed. So there are many GC algorithms. Here is a few of them. and there's a book, you guys probably know, the Bible of GC. And one that we're not going to go through here to this reference content, but it's a very simple one you guys probably know about. But these are one of the few algorithms out there when it comes to GC. So today, we're going to start off with going through a policy. The first one, GC, GenCon, which is a positives collector. And then after that, Johnny will talk about the breadth first scan ordering. And then after that, I'm going to talk about balance and the technologies that comprise that. So now, Jonathan is going to go through with you what GenCon is and what breadth first scan ordering is. Take away, John.
Before John starts...
Thank you, Igor.
Okay.
So let's first talk now about GenCon. So GenCon is OpenJ9's generational copying collector. So GenCon takes inspiration from the weak generational hypothesis that says that in general, objects die quickly after creation or live a long time. So GenCon focuses its collection on a small part of the heap, and if needed, we collect the entire heap to clean up long-living objects. So for GenCon, we also have GC native memory overhead for the mark map, work packets, card tables, and copy scan caches. So with GenCon, this will also provide a significant reduction to GC stop the world pause times. It introduces a write barrier for the remembered set, which I'll be talking a bit more about. And also has a concurrent global marking phase. So in GenCon, the heap is divided into nursery and tenure areas. So your nursery space will be for your short-lived objects, and your tenure space will be for your long-lived objects. By default, the nursery is 1/4 of the heap size, and tenure will be 3/4 of the heap size. So if you look here, you'll see that the nursery is also divided into two logical spaces. We have allocate and survivor. So objects are allocated in allocate space, and during a GC, surviving objects are moved to the survivor space. So initially, the split between allocate and survivor is 50%. However, the GC will dynamically tilt this so that allocate space can be up to 90%. So some objects, such as classes and in turn strings, are allocated directly in tenure space, as they're not expected to be long-lived. All right, so let's look at a program that has allocated objects to a point where allocate space is full, and so it's time to do a GC. So if you look here, your white arrows will be for your application thread. Red, you'll see soon, will be for your stop the world pauses, and yellow will indicate concurrent GC. So with Scavenger, so we've now allocated, and our allocate space is full, so it's time to do a scavenge. So Scavenger is a copying collector, where it copies objects from allocate to survivor space. And if objects meet the age threshold, the GC copies it to tenure space in a stop the world fashion. So after we finish with a scavenge GC cycle, the application can continue. And then once our allocate space were to fill up again, we can have another scavenge. So it's also interesting to note that we can have a concurrent global collection start as our application is running. So this is going to use a mark map to mark objects. So this global collection will concurrently mark tenure, and at the end of the global phase, it'll mark nursery objects. So after global GC finishes marking, we do class unloading, sweep nursery and tenure space, and then if needed, we'll compact tenure space if it's fragmented. So here you can see the yellow arrows indicating concurrent GC. We can also have a scavenge if our allocate space fills up again. Here's the concurrent GC marking objects in tenure, and then we'll hit our global end, and then our application will continue. So in GenCon, there's actually also a write barrier, and there's one specifically I'll talk to you about. So why do we need a write barrier? Well, you see the GC needs to be able to find objects in the nursery which are only referenced from tenure space. So that means we have to track all the objects in tenure space that have pointers to nursery to make sure that objects in nursery aren't erroneously collected simply because no object in nursery is pointing to it. So we look at this example, you're going to say, how is the right barrier implemented? And so if you look at this method called SetField, it's going to take an object A and object C, and what we're going to do is it's going to set the field A.field1 to C. So first what we need to do is check if A is tenured and if C is not tenured. So this is the case where we have an intergenerational relationship that wouldn't be found during a nursery collection. So now we need to remember A and remember this intergenerational relationship. Also, along with this, we need to know if our concurrent GC is active. So let's say A is tenure, and perhaps C is tenure as well. We need to check to see if concurrent GC is active, because if it is active, since these objects are both in tenure space, what we're going to need to do is check to see if concurrent GC is active so that we can dirty the card table for A, so that this reference can be found at the end of the global collection. And remember, we don't need to dirty cards for nursery objects since we don't mark them concurrently. They only get processed during the stop the world phase of a concurrent collect. So now just a little bit about Concurrent Scavenger. So Concurrent Scavenger is a generational copy collector. It's going to introduce a read barrier for concurrent compact, and it has a goal of being a pauseless GC. So with Concurrent Scavenger, again, your heap is divided into nursery and tenure spaces. Your nursery is then also again divided into two logical spaces, allocate and survivor. So similar to the example we looked at before, let's say our application thread is running, and then our allocate space fills up, and we're going to hit what we call a concurrent scavenge start. So this is going to be a very short stop the world pause to determine the root set for the GC. After this is done, what we can do then is start running concurrently and marking objects in allocate space concurrently with the application. Once this is complete, we'll have a very short stop the world pause where all GC threads are synchronized and cleanup can be done. And the read barrier, there's also a read barrier. And so this read barrier in Concurrent Scavenger is basically checking if the object has been moved or not. And if it hasn't, it'll move the object. So you can see we finish our concurrent scavenge end, and then our application will continue with no GC thread running concurrently. We have another concurrent scavenge start. Here you can see threads running concurrently, and then we have another end. Again, we can have a concurrent global collection start that'll start marking objects in tenure space. So with Concurrent Scavenger, we have multiple GC threads trying to move objects. As well, we have mutator threads trying to access these same objects. So you can see how we could definitely have some issues here. So let's look at an example. So here we have a GC thread trying to move an object and a mutator thread trying to access the object. So in order to prevent issues here, what we'll do is both threads will unconditionally copy the object. So here in survivor space, you can see we have two copies of the object. Both threads now are going to compete to place a forwarding pointer into the old object. So in this particular example, as you can see from the indicated by the green arrow, the GC1 at placing the forwarding pointer. And so what we're going to do now is, since the GC thread 1, the mutator thread discards its copy and follows the forwarded pointer to find the correct copy of the object, so we don't have multiple copies of the object. So many of these concepts that we've talked about so far lead nicely into this topic coming up next, and that's dynamic breadth first scan ordering. So this is a new optimization that works with GenCon and balanced GC policies. So I'll just go over some key concepts. We'll look at an example with GenCon with breadth first scan ordering, then take a look at an example with GenCon with dynamic breadth first scan ordering, and finally we'll look at some results and takeaways. So first, some key concepts. So let's start with the 90-10 rule. So this is a program spends 90% of its time in 10% of its code. Caching, this is storing data in cache memory, which is very fast memory. And it's also important to know that the data you decide to store in your cache memory can actually have a large performance impact. And I'll show an example soon. So cache prefetching, this is fetching instructions or data from the original source in slower memory to a faster local memory before it is actually needed, hence the term prefetch. So we have the caching hit to miss ratio. So this ratio describes the ratio of cache hits, so information in the cache is requested, to cache misses, information not in the cache is requested. So there's actually a strong correlation between locality and application throughput. So the more an application exhibits strong locality of reference, the more application performance optimization is possible through techniques like cache prefetching. And a little fun fact that will help you kind of see the importance of locality is that the runtime of different matrix multiplication kernels that perform the same number of arithmetic operations, but have varying degrees of locality, these runtimes can actually vary by a factor of 20, which is pretty crazy when you think about it. All right, so according to the 90-10 rule, so let's say if 90% of the time is spent in 10% of the code, we likely have some very hot object access patterns and very hot fields. So a hot field is a field that's frequently accessed by an object instance. So for example, if you take a string object, a very typical hot field would be the char array, as typically when you access a field of the string object, you're accessing the char array. Another example of this would be the hash map node and the field's key and value. Typically, for the most part, when you're accessing fields of a hash map node, you'll be accessing the key or the value. So a hot access pattern is an object access pattern or path that occurs frequently. So lots of hot field information is actually known by the JIT, which is the just-in-time compiler. But how can we exploit this information in order to improve locality and in order to make caching and prefetching more effective? All right, so let's look at an example here. So this is a very common object access graph that could occur. And so just to break down what you're seeing in the diagram, you have object A, which has two fields B and C. And when a field of A is accessed 90% of the time, it's C that gets accessed. 10% of the time, it's B that gets accessed. Looking at object C, when a field of C is accessed 10% of the time, F is accessed 90% of the time, G is accessed. And then again, looking at object B, when a field of B is accessed 10% of the time, D is accessed 90% of the time, E is accessed. So if you look at this graph, how would you like to optimize it for locality? So ideally, we would have A, C, and G spatially localized in memory, and B and E spatially localized in memory in order to render locality-dependent optimization mechanisms like caching and prefetching more effective. So let's look at an example with GenCon using a typical breadth-first scan ordering policy. So after a GC cycle with root set AF and the object graph shown, the heap would look as follows. So if you see, here's the initial object graph and with two different visual representations of it, and here's the final representation after a GC. So you can see how objects moved using a breadth-first scan ordering policy. So scanning objects breadth first. So I'll breathe through the steps here of the scavenger GC cycle. And we'll look at another example soon where we'll get more into the intricacies of scavenger. But for this example, it's really to show the following. And so with common access patterns of ACG and BE, the existing breadth-first scan ordering implementation is clearly not optimal with regards to locality if we're trying to maximize the likeliness that objects referenced frequently together, like ACG or BE, are in the same cache line. So how can we leverage existing infrastructure to improve locality of these hot fields? And that's where you see the goal of dynamic breadth-first scan ordering. So dynamic breadth-first scan ordering is to optimize breadth-first scan ordering for improved locality. Since various object field information heuristics, those are known by the JIT. So what we want to do is leverage this information to force potentially improved object locality. And then this will ideally render locality-dependent optimization mechanisms like cache prefetching more effective. And remember, better locality in modern systems leads to better application throughput. So I'll just talk now briefly about some relevant existing infrastructure that you need to better understand in order to properly understand how dynamics breadth-first scan ordering will work. So most importantly, what is a compiler, what is an optimizing compiler, and what is dynamic compilation? All right, so first, what is a compiler? Well, simply it's a translator. So it's going to take code written in one source language and will produce equivalent code in another target language. So possible source and target languages are source code and machine code. You can have a compiler like GCC or Clang. You can have source code to bytecode, where the compiler like Java-C. And then you can have bytecode to machine code, a compiler like the Testarossa Chit in OpenJ9, and many more possible examples. So next, what is an optimized compiler? Well, this is a compiler that tries to produce good code. And by good code or optimized code, it means code that should execute faster, require less memory, and consume less power. Next, what is dynamic compilation? Well, this is when the interpreter invokes the compiler just in time before a method becomes a performance problem. So the just-in-time compiler will turn bytecode into much faster native code. So Eclipse OpenJ9's Testarossa JIT compiler is an example of an optimizing compiler. All right, so let's now talk about some other pieces of relevant information in JIT compiler infrastructure that gets leveraged with dynamic breadth-first scan ordering. So first, we need to understand that applications consist of compilation instances. So that is logical compilation entities, like i.e. methods. So the JIT compiler is a tiered compilation compiler, meaning that each method starts at a base compilation level, and the JIT can decide to optimize a method further based on various heuristics that relate to how frequently the method is run, as long as other heuristics. So the Testarossa is an optimizing compiler for OpenJ9, and it has compilation levels cold, warm, very hot, hot, and scorching. So each compilation is divided into blocks where the relative hotness of each code block within the compilation is determined, and blocks receive a normalized block hotness value of 1 to 10,000. 10,000 being the hottest block in the method. So when a field is accessed within the compilation, we can compute an overall hotness value approximation for the field access using the compilation optimization level of the method and also the block hotness of the block within the compilation where the field was accessed. And then possibly in the future as well, there is a goal to have it include CPU utilization of the method block as well. So there'd be for sure some roadblocks here, but this would be something very interesting to be able to integrate into the existing calculation and would certainly have potential. So this hotness value is computed for every field access of every compilation in a very efficient manner. So for every field of a class, we can aggregate these hotness values for all values accesses across all method compilations and get an approximate value for the hotness of each field of a class. So that was a mouthful, but let's look at an example now that will more visually show this. But first, I should mention that hotness values of a field in a method are aggregated via a user-selected hotness algorithm. And then so knowing the approximate relative hotness of all fields of a class, thanks to leveraging heuristics and information available from the JIT, during the GC, when an object survives the GC and is copied to the survivor space, what we're going to do is we're going to recursively depth copy the object's two hottest fields directly after the object is copied, if hot fields for the object exist, meaning these fields have crossed the minimum hotness threshold. So this is done in order to avoid excessive depth copying of fields that truly aren't hot fields. So now here is the example I was alluding to before. And so let's take a look at this example for a class string with the char array field. So in this example, we're going to look at the char array field where it has been accessed in 3 different methods. The first with a compilation level of hot, that we give a compilation level weighting of 10 for a hot method. And then let's say where it was accessed within this method was in a block that was given a hotness of 50. So what we'll do is we'll multiply this together, and this is again a simplified version of dynamic breadth first, but it does illustrate the point well. And we'll see that the hotness contribution of this field access within this particular method A has a hotness contribution value of 500. So next, method B has a compilation level of scorching. We'll give that a weighting of 100. We'll say it was accessed in a block that was given a rating of 40. And then this hotness contribution from multiplying them together is 4,000. Next, in method C, we'll give a compilation weighting of 1 to a warm method. This was accessed in the block that was given a rating of 1,000 for the hotness of the block within that method. And this from multiplying them together, we'll get a hotness contribution of 1,000. And then now we can see we can gain a approximate value for the hotness of this field relative to other fields of the same class. So this value, hotness value for the char array field of a string is 5500, which we can then use to compare with other fields of the string. All right, so let's look at an example now of a scavenger GC cycle, but this time we're going to use a dynamic breadth first scan ordering policy. So for this example, we will only depth copy the single hottest field, although there is an option to copy the single hottest field, the two hottest fields, or the three hottest fields if you like. It's also worth noting that actually for this example, and for the sake of clarity, the name allocate space will get used interchangeably with the name evacuate space. And this is because during a GC, the allocate space will have its live objects evacuated from the space to the survivor space. All right, so the first thing is to scan the root set. So we have this given root set AF, and then we have this object graph as shown with field percentages, field access percentages as well shown. Same example that we've looked at before. So the first thing we need to do is scan the root set. And so in OpenJ9, this is going to be made up of class objects, class loaders, intern strings, JNI global references, thread stacks, and objects that are waiting to be finalized. So there's also an extra root called a remembered set, which I mentioned before, that I would talk a bit more about. So this is used to keep track of references between tenure and nursery space to ensure that these nursery objects are kept alive, if you remember from the example we looked at previously with the right barrier. So from scanning the root set, we're going to find more objects, and then from scanning those objects, we'll find more live objects until all live objects are discovered. And then all remaining objects you can declare to be unreachable and can be cleared. So how exactly do we do this in GenCon? Well, we have what you would call a per thread work list. And this is, in this work list, we have a scan cache and a copy cache, which are both fairly obviously named. So the scan cache is something that you'll be scanning in the future, and the copy cache is somewhere you're copying into. And this is actually just a pointer to some place on the heap, as you'll see in a moment. So each GC thread doing work will go and reserve chunks of memory so that it can copy without having to hit locks or anything like that. So similar to how allocation works in a TLH or thread local heap. So the copy cache is basically a direct mapping, as you can see, to some place in survivor space. So objects actually in OpenJ9, they're going to be aligned so that all the addresses have the two least significant bits to be 0. And so the GC uses these bits to represent forwarded objects, which will be used so that a thread trying to move an object from evacuate space to survivor space can check to see if the object has already been evacuated. So looking at this example, we'll start with the root set. We'll copy A to the copy cache, and then we're going to atomically swap in a forwarding pointer at the old location to point to the new location. And like I mentioned before, this will prevent another thread from copying object A again later. So also know that for simplicity's sake and to avoid confusion from having too many arrows, I won't be showing forwarding pointers for this example, as it'll just get too messy on the diagram. And also you should note that there are some steps that are missing. So I've shown all the key steps in this example, but there are some steps with GenCon that are left out to keep things simple and understandable. All right, so now what would we typically do is move on to copying F. So if you look at our root set, we have object AF, we've copied A, and typically what we do next is copy F. However, what we're going to do now with dynamic breadth first scan ordering is we're going to check to see if A has any hot fields. So after doing this, we find that A has hot fields C. So what we're going to do is we're going to dynamically copy C. So now again, instead of continuing on the root set to F, we will dynamically check C for hot fields. And from doing this, we're going to find G. So we're going to dynamically copy G. Since G does not have any hot fields, we can then continue back to the root set from where we deviated from our dynamic breadth first, from our breadth first scan ordering. So we were scanning objects breadth first, and then we deviated from breadth first to dynamically copy objects that we thought were hot fields. So that means after scanning A, we'll next be looking at F. So now we're going to copy F, and since there are no hot fields for F, we're now done with the root scanning. Now that we're finished with the root set, we need to publish our copy cache so that another thread could use it as a scan cache, or perhaps we could use it as a scan cache. So anytime your list is full or empty, you're going to push or pop to these lists. But if you finish one of the GC phases, like root scanning, each thread will flush their caches so that work becomes available for all other threads to share. All right, so now that root scanning is complete, we need to scan all objects on the work list until the list is empty and all reachable objects are found. So starting off, we're going to grab the first item off the work list. So here you can see I've copied this into both the scan cache and the copy cache, and I've done that for a reason. And that's to highlight that if there is some remaining space in the cache, we're actually going to use this cache as both a copies cache and a scan cache in an attempt to copy objects closer to the references in memory, which is another optimization that's centered around locality. So now scanning object A, we will find object C, which has already been copied. And then B, which has not been copied, so we'll copy B. Now again, instead of continuing along the scan cache to C as we typically would, we're going to check B for hot fields. And there we're going to find E. So we'll dynamically copy E. Since E does not have any hot fields, we can once again continue from where we deviated from our typical breadth first scan ordering. This brings us along the scan cache to C. Since references F and G of object C have already been evacuated, we can move along the scan cache to G. Nothing to evacuate for G, so we'll move to F. Nothing to evacuate for F, so we'll move to B. And then scanning object B, we're going to find object D, and then copy that. Nothing to evacuate for E, so we'll move to D along the scan cache. And then here we have nothing to evacuate for D, so we're finished. So theoretically, we would then start to pull more items off the work list, and the GC scavenger would continue. But for the purpose of this example, I'll stop here, and we're going to compare the results of dynamic breadth first versus breadth first on this particular example. So before I do that, here's just a summary diagram before and after the GC. You should also see that after we completed this scavenge with the given root set and object graph. We're going to complete a tilt, as I mentioned earlier, where we can tilt up to 90% of allocate space to make room to allocate more new objects. So we're going to do this in our allocate space. All right, so let's look at breadth first versus dynamic breadth first now on the same slide. So with common access patterns ACG and BE, it's pretty clear that dynamic breadth first scan ordering is more optimal with regards to locality if we're trying to maximize the likeliness of objects referenced frequently together, like ACG or BE, in the same cache line. So this may not appear to be significant. However, these potential wins can really add up. So to reiterate, with higher potential to have objects frequently accessed together, spatially localized in memory, this will likely lead to a higher hit to miss ratio for the application with dynamic breadth first scan ordering as opposed to breadth first scan ordering. And as I mentioned before, better locality will likely lead to better application throughput. So if we look at some basic results we've seen so far for dynamic breadth first scan ordering, we've seen a 2 to 8% throughput improvement on various benchmarks, a negligible difference in application compile time, a 2 to 3% increase in average application GC pause time. And as a side note, I want to mention that future development iterations are going to be optimized to reduce GC overhead while continuing to improve application throughput efficiency and try to improve locality. So this is the first iteration of dynamic breadth first scan ordering. And like anything in this industry, every first iteration always can be improved. So just a quick summary now of dynamic breadth first scan ordering. So we leverage existing JIT infrastructure. Every method is divided into logical blocks, where each block has a frequency value associated to it that's normalized between 1 and 10,000. If a field is accessed in a block with a block frequency above a certain block frequency threshold, along with other qualifying metrics, this field is reported as hot, and this data is factored into the overall hotness value of the field. The overall hotness of each field depends on 2 key factors that get accumulated and aggregated after every field report in every compilation. So this would be the block frequency of the compilation block of the field, where the field is reported in. So again, that's the block frequency of the compilation block the field has been reported in. And then as well, the tiered compilation level that the compiler is currently compiling the method at when the field access has been reported. So that would be your cold, warm, hot, very hot, and scorching. So of course this isn't going to produce a perfect copy order, but this can be much better than pure breadth first scan ordering and could really lead to performance wins for your application. So that's all for dynamic breadth first scan ordering that I'll talk to you about today. And now I'll pass it over to Igor, who has many more exciting topics to cover.
Awesome. Thanks. Before you pass it on to Igor, can I ask a minor question? So how large did the change sets to the JIT compiler end up being? Were they anyhow significant?
So the change set to the JIT, those were actually quite minor changes that needed to be made, because there was so there used to be an existing way of using hot fields, and so this way of using hot fields was very, very simplistic. So we had access to very good data, as you can see from how we were able to leverage a lot of this. But how it was previously leveraged was for some very, very basic optimizations that led to almost negative, which almost had a negative impact. And many applications did have a negative impact. So it was just the way a lot of the infrastructure was there, just not leveraged, not leveraged appropriately, you could say, without getting into too much detail.
Okay, cool. And one more to follow up right away. So as I understand, even like the JIT compiler threads, they didn't end up allocating much more or doing much more computation. Did I get it right?
Yes, that's correct. So there was, as far as JIT compilation times goes for the methods, those saw with various benchmarks that heavily stress tested startup and compilation times, those saw a negligible difference in times that led to that could all be explained away through any sort of error. So within 0.5%.
Cool, that's really impressive. So I'll just remind one more time to the audience. So please, there is a button somewhere in here that invites you to the Telegram chat. Please just click it. You can ask questions there. You can chat with the experts via myself or via Volker. We would be happy to get questions from you. So far, there are no more. And please, to go on, I guess, Igor. I'm not sure I can hear you, Igor. Are you muted by any chance? Just a moment. Yeah, we still cannot hear Igor. We are looking into the problem, and I guess it's going to be solved momentarily. Perhaps, meanwhile, we can get another question. So there is the heuristic of checking if the field is hot. And is it anyhow configurable at startup time or at runtime? Yes, that's to John.
Yes. So there are a lot of I guess we use them. I use them during the implementation phase, and they're still existent, but they're not just because they've been used for further testing the implementation. It's not recommended that
can you hear me now?
That it is used for tuning. So there's some actually a lot of really interesting different features that have different. For example, you can modify the amount of hot fields you're going to depth copy. You can modify the depth that you're willing to depth copy objects. So by default, it's set to 2, which is a good to stick with. But you can, if you have some very deep copy paths in your application that are getting heavily used, you can up that. So there are many more in terms of how long you let your field lists go and your minimum threshold for hotness of fields that can be modified. And so there are many different ways you can adjust your metrics to the specific benchmark or application. But for the most part, these values are probably not wise to mess with unless you have a deeper understanding, or unless you just want to try some trial and error.
Cool. That's really impressive. Cool. And it looks like Igor is back. Can you say something, Igor? Let's see.
Yes, I think I'm back.
Yeah, cool.
Then let's get on with it.
Also, I'll take it away then. All right, thank you, Johnny. Thanks for sharing with us breakfast ordering. So what's a live presentation without technical issues, right? So here we go. So I'm going to first talk about balanced policy, and then I'll talk about double mapping, and after that, off-heap management. So if you're familiar with the G1 policy from Hotspot, they are very similar to each other. So they are both region-based collector. They're both generational. One big difference here that I can think of is that balance has, I think it's 27 edges, while the G1 has three edges, but they're very similar to each other. So it provides significant reduction in max GC top of the row pause times. It introduces a write barrier to track inter-region references, similar to the one in GenCon, because here we can have references from different regions going to one region. So we need to keep track of those somehow. And there's a incremental heap defragmentation because of the way that balance works. So like I said, the heap is divided into regions. Here we try to allocate between 1,000 to 2,000 regions. Therefore, the bigger the heap, the bigger the region size. We allocate objects on what we call add-on regions, as they are just another name for new regions. We try to allocate objects in the region that's close to your NUMA node, if the system supports NUMA node, which is pretty cool. If an object is larger than a region, we actually turn out of memory error with the exceptions of arrays. So if we have an array that's larger than the region, what we do is we allocate as an arraylet. So what is an arraylet? So what we do is chunk that array into different parts, put that, say, a part here, another part here, another part here. And in the header, we have pointers pointing to these different parts. So this is just a nice way to allocate large arrays into this region-based heap. So this is how an application would behave under this policy, right? So the white arrows there is the application thread, and the red arrows is GC thread. So PGC stands for partial garbage collector. It's simply a copy collector that's going to be copying objects from one region to the next. This copy collector looks for those regions with the most return of investment, meaning those regions with large amounts of garbage. Say a region has only one live object. All it has to do is copy that object over, and then voila, we have an entire free region for us. So it's a copy collector, stop the world. The problem with GMP is that it only has local information about the regions it's collecting. And with time, it loses this information. Therefore, and GMP, which stands for Global Marking Phase, is there to help PGC update its local information. So GMP is actually building an accurate mark map for the PGC. So whenever GMP is done, it updates PGC information so that PGC can make better decisions on which regions to collect. So a little bit more on this global marking phase, right? It does not reclaim memory. It only performs marking phase, like I said. It can run between PGCs, and it builds this accurate mark map of the whole heap because it has the global information of the heap. And after this GMP is done, it's going to use this accurate mark map to update the information about in PGC. Then after that, PGC is going to be like very up to date and defragment the heap. So what I mean by defragment the heap. So this is a graph representation of the application on the balance policy. So on the x-axis we have time, and the y-axis we have free heap. So lines going up is the garbage collector collecting objects, and lines going down is the application consuming memory. So you see this trend going down, right? Is the PGC losing this local information? So if that trend continued, we probably hit out of memory error. So GMP knows where to trigger so that it finishes in a timely manner to update PGC's local information so that it can defragment the heap. So you can see around in the middle there somewhere this trend going up. That's the point where GMP updates the PGC's local information. So PGC has fresh information so that it can actually defragment the heap, which is why you see this trend going up. And after a while, it's going to lose this local information, and this trend going down is going to start again, and then we would need to trigger another GMP, and the process repeats from there. All right, so the right barrier here, I'm going to go quickly here. Like I said, we needed this barrier because we might have this inter-region references, right? And here we chose to, because whenever we design barriers, it's always a trade-off, right? Should we put the burden on the GC threads or on the application threads? So here we have an unconditional barrier. So we actually chose to put the burden on the GC thread. So whenever the GMP is active, right, or what we do is just dirty that card unconditionally, the application thread, right, so it doesn't have to worry about checking inter-region references and all that. So it just dirties the cards unconditionally, and then it tells, okay, GC, you take care of that. So at the beginning of the PGC goes through each of these dirty cards and checks for these inter-region references, and if there is, we then add that to the remember set card list. So that's how we remember these inter-region references and balanced. So Arraylets. So this is a good segue into this technology, the double mapping. So first I needed to talk a little bit more about arraylets. So this is a technology to allocate large arrays into this region-based heap, right? And we use the spine to allocate the spines allocate like a number of objects, and it's going to have references to the actual data of the heap. And this data that's going to be the heap is what we call leaves. So this is a graphical representation of what I'm talking about. So in the bottom there we have the arraylet header, and on the right of the header, which the header is just going to be the class and the array size, we have the data references, right? And those data references actually pointing to the arraylet, to array data. So imagine we want to access the first element of this array. We would follow that first data reference, go through the last blue box there, and access the element right there. What if we want to access the last element of this array? We would follow the last data reference there and access that middle blue box right there. Right, so it's a fairly straightforward concept here. So this is a simplistic representation of how it looks like on the heap. But in reality, it kind of looks like this, right? Here I just put like some more objects. The technical name for these data references is what we call arraylets, right? And on the heap, you're going to have all the objects and all that, but this is the high-level representation of how an arraylet look like with this cool concepts of you have to this indirection to access data for the array. All right, but there's a problem here because some APIs require a contiguous representation of the array, which is not the case of arraylets because they are all over the place, right? So this is the case for Java native interface, critical APIs. If you're not familiar with them, these critical APIs used for when the programmer wants direct addressability of the objects. Hence, it needs a contiguous representation of the object. So what do we do now? So actually, what do we use to do with whenever we are faced with such API? We would actually create a temporary array, contiguous array, and then we would copy element by element to this temporary array. This is starring, yeah. And then we would pass this temporary array to the actual API. The API would maybe do something with this array, modify some of these elements, and then at the end, we would copy everything back to the original array. And as you can imagine, this is very expensive. So the trick here is double mapping to the rescue, right? So the trick is to make this contiguous arrays look contiguously. So we came from the fact that physical memory is limited, but virtual memory is not. So in 64-bit systems, we have 2 to the 64 worth of bits of memory, which is very large. So we can use that to leverage this. And you're familiar with ZGC. ZGC uses similar technology. They use multi-mapping to keep track of in which phase the objects are in the GC phase. And here we just use for this to have this contiguous representation of the array. So the trick is we map 2 virtual memory addresses to the same physical address. And the good thing about this is that any modification to one virtual memory is going to be reflected to the second virtual memory address. So how does it look if I were to graph this? So in the bottom there, we have the original array, right? So we double map this contiguous array in such a way that it's going to look contiguously in memory on the second virtual mapping. And the nice thing about this is that any modification to this contiguous mapping that you see on top is going to be reflected on the original one. Therefore, we don't have to do that expensive copying back and forth for this API that requires contiguous representation of the array. So this is pretty cool. So, and comparing the Gen9 critical operations, we got like 30 times boost in speed up when it comes to like array operations, which is really nice. But can we do better? There's some issue with double mapping because it's only available in new version of Linux, and we are actually working on right now on a new technology called Off-heap management, which is we're gonna talk more about right now. But before that, here are some of the double mapping drawbacks, right? So in order to make this possible, there's two system calls, shimopen or memfdecreate that we use. Both of them creates a file descriptor, and you know that all systems have a limit on the file descriptor that can be used. Shimopen has another drawbacks that it's going to use shared memory, and by default in Linux systems, there's a limit on the shared memory you can use, and that's half of the physical memory. And the drawback of memfdecreate is that it's only available on newer glibc versions. So either of them, multi-mapping is great, but there's this little drawbacks. All right, so off-heap to the rescue here. So this one does not require file descriptors. It also takes advantage of this vars virtual memory space in 64-bit systems, which is why it's not available on 32-bit systems. Won't be available. So how this off-heap looks? So this is just a specific name for a secondary heap where we would allocate this large array. So instead of allocating this large arrays in heap as either arraylet or double mapped, we would actually store this array at the secondary heap as you see it here on the screen. And then we would put the data pointer, the data address of the data of the array in what we call proxy object, just a fancy name for the array header with this object pointer that's going to be pointing to the data at the off heap. This is a more complete representation of what off heap would look like. This is actually the original idea. The solution that we implemented is a bit different, but imagine we have this huge off heap, and it's so big that we are sure that we'll never ever have to compact it, because we all know that compacting the heap is very expensive. So we leverage this large amount of virtual memory so that we reserve big space so that we never ever have to compact the heap. So that brings me to a question here. So what's the smallest off heap that we can come up with so that we'll never have to compact it? So let's be greedy here. So we can just take the in-heap size multiplied by the region count, and that will actually be enough to have a large enough off-heap to never ever to compact it. So here in the example, say we have a 2 terabyte heap with 1,000 regions, we would have a 2 petabyte off-heap, which is large, but still manageable for 64-bit systems, right? But we can do better. So what's the worst possible allocation pattern we can get? So imagine the following scenario. We are allocating regions, arrays of size 2 regions, right? And that array is going to be allocated at the off heaps, right? So we allocate a bunch of those in the off heap, and then after they're all allocated, we free every other object. So we're going to get something like the third line there. We free one, keep the other one, free one, keep the other one. So we are left with these two regions free there. And then the other pattern will be we now allocate arrays of size 3. So since they cannot fit into these 2 free regions, they have to put all of them after the last one, just like it's in the last line there. And then after that, we free every other region, every other array as well. And after that, we're going to be left with free sizes of 6 regions, right? And then after that, we allocate objects of size 7 because 7 cannot fit into those 6 regions there. So we have to put that after the last array as well. And you can see, and that trend continues, right? Allocating all these large arrays that cannot fit into this Swiss cheese heap that we have been creating. So there is a pattern here, and we can actually come up with the upper bound as for the size of the off heap. So in the bottom there, we have our greedy solution where we ended up with a 2 petabyte region, right? So if we're smart, we can come up with this nice equation here, the ceiling of the log of 2 of region count times the heap size divided by 2. So we are guaranteed that if we have that size of off-heap, we'll never ever have to compact the heap. So in this example here, instead of having 2 petabytes of heap, we actually end up with a 20 terabytes of heap, which is a lot better than 2 petabytes. So here's some positives and negatives of this technology here. So this is going to be supported by any platform that supports virtual memory, 64-bit systems. It unburdens the in-heap to store these large objects. The off-heap will never have to be compacted, which is great. And it does not require any file descriptors. But on the other hand here, well, some negatives. Whenever we commit memory at the off-heap, we must decommit memory at the in-heap, because if you don't do that, we might actually surpass the limit of the max memory allocated by that application. So we have to do this committing and decommitting of memory as we allocate memory at off-heap. And another negative, there's one extra level of indirection to access the array data, which is the data pointer at the header of the array. Cool, so I'm almost done here. So before summary, I just wanted to show this really nice chart that I put it together, which shows like the similarities between the different GC, the most famous GC policies out there. So on the right there, we have some of the hotspot and Red Hat, and on the left we have the ones from OpenJ9. So in yellow we have the common GCs, right? So GenCon, CMS are really similar to each other. They're both generational. They both have neo and old space, right? They both have a copy collector. Balance and G1s are very similar to each other, as I was alluding to before. They are both region-based. They're both generational. They also have a copy collector. And in the blue region there, the lines are thinner because they try to achieve the same goal, but they're not as similar to each other there, right? For instance, metronome, as you see, they're both region-based. They use different barriers. For GenCon CS is kind of similar to Shenandoah because they, at least for Shenandoah version 2, because they use the same read barrier. For Shenandoah version 1, they use a Brooks pointer, which is not the same as GenCon CS, right? But they all try to, they all have the same goal, which is reducing the pauses of GC. And then in green there we have Azure C4, which is also a pause of GC, but it requires special hardware or software. So in summary, here's just a quick, a nice, summary. You probably know this. If you don't care about GC pauses, right, you should go with a perfect stop-the-row GC, because that's going to have the higher throughput, because it doesn't have to worry about all these barriers, all these overhead to keep track of this concurrency, right? But if you do care about pauses, then you should go with the perfect pauses GC, because that's going to have the lowest pauses, but because of read and write barriers, you're going to have lower throughput. So today, Johnny went with you today to Dynamic Breadth First Outlining how we use this object information, like how hot is its objects fields to scan through those objects. Then I went through with you with double mapping and off-heap object management, which are two ways that we use to better allocate large arrays in region-based GC policies. So here are some links, OpenJ9 on the top there, Oommen on the bottom, and up top OpenJDK if you want to get some of the builds there and play around with. Feel free to connect with us on social media. And this is the book I talked to you before. And there's the GC Bible. But yeah, I think we are top of the hour, and I'll finish off here and see if anyone has any questions.
Awesome. Thank you so much. It's really impressive. Great work. In terms of questions, there is something that I immediately wonder about myself. At first, in John's part, you mentioned that basically if the object size is larger than the region size for non-arrays, you would just throw an out-of-memory error. Is that does that really happen often in production? Do people complain?
I don't think it does. Actually, I never heard about anyone complaining about an object that's larger than a region. It's common for arrays, right? Because you huge array for whatever reason, but I cannot, because imagine you have a heap of size 1 gigabyte, sorry, and you divide it by 1,000. You're gonna have half megabytes of 500 megabytes. No, wait. 1/2 megabytes, which is very large regions, right? So I can think of an object that can span that big, right? So, but I never heard about any situation like that before.
All right. Yeah.
I think the number of fields is bound, right? I think you cannot have more than 64,000 fields in a Java class.
Okay.
And if you multiply that with 8 bytes, you think you get you cannot get bigger than
yeah, that's
8 times 60, but it's like 512K or something like that.
Yep.
So I think that's safe.
That sounds about right.
Then it makes me wonder why G1 really needs to have humongous objects and their regions. But then again, we are kind of running out of time, so we can take this to the discussion zone. Thank you a great deal. Everyone is most welcome to join the discussion zone with the link here or the link that you will get in the Telegram chat. Thanks again, and see you soon.
Thank you. Bye-bye.
Bye.